Hey, Huddy here. I thought with not being able to get out as much, you might like to investigate what's going on. So, social distancing, I guess you know a bit about this. There it is up there. It means keeping your distance when you're out in society. And safe distance, they reckon, is 1.5 to 2 metres. The idea is to stop the spread of viruses. And the one we're fighting now is, of course, the coronavirus. Hey, not like these guys. Packed in like sardines. This photo was taken in the United Kingdom before the virus struck. And this scene is not unusual in big cities where there's a high population density, like many people in a relatively small volume of space. So why don't we go for a walk now into in Times Square in New York City. So here we go. Times Square, New York in 2015. Hey, London and New York have about 9 million people in their cities. That's about a third of the population of Australia. And Beijing has got 21 million people in that city. That's almost the whole of Australia in one city. Oh, wow. Let's have a look here, though. Have a look around. It looks like people are dressed fairly casually. It might be a holiday. Police are there, maybe having a march or some carnival or something. But have a look at the skyscrapers. The city goes on forever. I mean, we're just going to look around Times Square, and New York's a lot bigger than that. Have a look. You'd fit thousands of people in those buildings. We'll cruise down here for a while and have a look. A lot of sightseers go to New York, of course. I've never been, but they reckon that's the big venue, one of the big venues to see if you're a tourist in America. The Big Apple. Before the virus struck, it didn't ever sleep, I don't think. It was open 24/7. People looking up at something. There's a live video of the crowd. You can wave to yourself there. All happening in New York in 2015. Al fresco dining there. No dining at the moment, unfortunately. Coming up to cinemas, office blocks. Wow, there's a big building. There we are, 2015, 5 years ago. New York Police Department over there. Cinemas and stuff. Hey, getting a bit more crowded here. I've jumped ahead a bit. We'll continue our journey down Times Square here. All shapes and sizes, all age groups there. Cruising around, having a look. Getting a bit dense now, isn't it? We're getting on top of each other a bit. They're getting close here. You don't want to have anybody sneeze. Hey, about now, I bet you would like to live in a small country town way out in the spaces of Australia. What do you reckon? Bit safer, eh? We'll leave that now. So welcome back let's have a look at what we can do about the maths of what's happening around the place at the moment. So come down to the next screen now here, and we'll have a look at mathematical modelling. Wow, what's that? Well, mathematical modelling is what people are doing a lot about now with a virus. They're trying to use maths to describe a practical situation, what's really going on in our world with the number of people getting the virus and that stuff. So we're going to try and do a bit of that at a very basic level. We're going to use maths to describe a practical situation. So our first task is to build a model to describe what's happening. Let's try to make up a table. Here it is here. I've started one for you. And I've got some little activities in here that you can go on with and talk to your brothers, sisters, family members, because you're all sort of cooped up at the moment. Now, where there are lots of people in big cities, we looked at how many contacts a day would one person make, you reckon? And how many of those contacts would spread the virus through sneezing or touching? Now, I've drawn a little graph down here, so it's all part of our mathematical model, if you like. And you might have seen a graph like this before, where we've got one person here who has the virus on the first day. And we're going to say, well, how many people do you think that person would transfer the virus to? Now, that's not just contacting people. That's some contact where the virus would be spread. So droplets, sneezing, that sort of thing. I've suggested to start our model, we could say he or she who had the virus spread it to just three more people in a day when they were contagious. So this is oversimplified a little bit because we're saying that the person was contagious and that they spread it to 3 people in that day. And of course, in the early days of the virus, people weren't aware of what was happening, that they had this virus. And so sneezing and that wasn't as big an issue as it is now. So what we're going to say here in our model is, on the average, let's say each person who gets it now, on the average, also has the same number of contacts where they spread the infection. So 3. This person will have 3 contacts, let's say, where they have spread the virus. Okay, so I want you to complete this diagram for quite a few more days out here. Okay, and see if you can see a pattern. And like in this one here, we would have up here 3 more people were infected that day. Notice it's a number of people infected day by day. Okay, now you might see a pattern as you do a few of these. Depends on how much maths you've done. If you're only junior level maths, then you might have to keep filling these out by drawing bigger and bigger diagrams. Hard way of doing it, but see if you can find the formula for maybe 4, 5, 6, 7 up here. Is there a way of working out what's going on so that you can fill in how many people would be infected on the 7th day? Just the number of infections increasing per day, just that increase. Okay, and we're going to assume it's 3 people like we've got here on the average, that every other person who gets infected infects another 3 people the next in a day. Okay, you'll see something here, I think, in that pattern, and this is called an exponential function because the number that grows each day is a power or an exponent of something. Okay, depends on how much math you've done as to how involved you want to get in that. So there's your first little task, and I want you to try and do that. You can talk to your family members about it, involve everybody so they can see what's happening around the world these days. Okay, come down to this next little slide here, and here we're going to do something slightly different. I don't know whether you've realised, but with the news streams about the spread of the virus, they don't say always the daily increase. They do, but look at this up here. We want the total number of people infected as time goes on. So do you get the idea? In day 1, there was only 1 infected. In day 2, that person infected 3 more. We now have a total. You had to add them up. There are the new infections on day 2, the 3 people, plus the original one. So you've got to do all the sums here, adding on the new infections each day, so that you can get a total. Here it is. This is the difference between the two tables, the total number of infections. Now, you could keep adding them. That's pretty long-winded, but there is a formula. So come down here, look at this formula here, our formula for the sum of adding up all of them. So it's the first one, so the A number is 1, the first term, and then it's the ratio. Now, what's the ratio? What did they go up by? It went up by ×3, didn't it? So the ratio is 3, and you raise it to the nth power. This is where we're getting an exponential growth now. So if n was 2, it'd be 3 to the 2, be 9, take 1, is 8, over r take 1, 3 take 1 is 2, which is 4. Now this might be getting a bit hard for junior maths, but that's a formula way of getting that entry there without actually mechanically adding them on. Okay, r is the ratio, which we're going to say is 3. You might like to do other models where the spread is more than 3 contacts a day, and the number of terms is the number of days. Now, I've got here a link to where I've discussed this in Huddy Maths on YouTube, and because you might like to say, "Oh, Huddy, where'd that formula come from?" And if you're into mathematics, you could either follow this pathway, Huddy Maths playlist, Models of Growth Part 3, Geometric Series, starting at 11 minutes on the video, or do you want to come and have a quick look at that and see what we can... So here we are about the 11th minute mark, and I'm talking here about the structure of all these numbers that we're adding up. It was 1, and then it was 1 times 3, 1 times 3 squared, wasn't it? Something like that. So I'll leave you to look at that and see how I develop the formula for adding them all up. But we'll leave that now. And here we are back at that page. So you might like to look at that or just leave it. If you're a more junior mathematician, you might just like to get the hang of adding them up and see what happens. Now, what I want you to do, the next little activity, is to draw a graph showing how the total number of people infected varies with time. You could do it by hand using graph paper, or you could use a graphing package like Excel or GeoGebra, or use a graphics calculator. So your graph should look, I think, something like this. What do you think? Now, you'll need to put something here. What are the axes going to be? Have a look up here. You're looking at the total number of people affected and time, so you need a scale as well along here. So you need to put a scale in along each of those. So there's your challenge. We're going to try to make a graph. So see where we're developing our mathematical models here. We're trying to describe what is going on with this virus spreading. Okay, do you get the idea? Okay, you can pause the presentation anytime and go back and check it out and talk with brothers and sisters and mum and dad about it. Okay, let's go down now. But hang on, you might say, well, Huddy, what's going on? They don't have graphs that go straight up like that. Oh, no. We don't have that. What do we have? Well, the first thing to notice is, look at this. The proportion infected. The proportion is a fraction. The proportion here is a fraction of the total population. So they're dividing the total number of people infected by the total in the population. Well, we're not going to do that, but it's important to see the nature of the curve, even if we had the numbers of people here, the actual numbers of infection. I'll show you one of those later on. We have to ask firstly, what does this mean? It's not going straight up like ours did. It stopped here. And on day 2, for example, there was 0.2 of the population. 0.2 is 2/10, or 20% were infected. But then for some reason up the top, here it is down here, it didn't keep going. It stops and had a peak. Then it comes down. I want you to think about, in the world, what would be happening in a country if it peaked and came around? Why might the peak occur at that point, which is quite lower than the total of the population? Why didn't it just keep spreading? Why is the exponential function going to be turned around there in real life? What's our model say? Okay, how can we explain that and build it into our model? Okay, so what factors might affect the rate at which the curve decreases? This here. And what might cause the graph to be more like the blue one than the red one? Hey, this is a little bit different. It peaked at a lower proportion of the population. A lower fraction ended up getting it. And it flattened out. Oh, I think I just used a word that they've been using, haven't I? And also, another hint is keep in mind social distancing as you try to explain what might be happening to make these graphs different from each other and different from your one that went straight up. Okay, put your thinking caps on you and talk to your parents and brothers and sisters. That's what I want you to do, so you're really into this and you know what's happening to you. Okay, come on down. And here we are. Now, this is heavier mathematics, quite heavy now, so a lot of people can just leave this one, I think, and just go on to the next slide. But here, the function that mathematicians use to try and describe this behaviour is this function here, or various versions of it actually, but it's called a surge function. And so I thought you might be interested in trying to get a graph drawn like that does turn around. And it's an interesting looking function because it's variable t, or you could call it f of x, but variable t occurs there and there. It's an unusual function because that variable occurs in two different positions in the function statement. So that's a variable there and there. So you might like to try to create a graph like that by using a graphing function. And you might also play with these numbers. You could play with that number and see what that does as you change the value of the variable as time goes by. So t here stands for time. As time goes by, what's going to happen to the number of infections? So you could use a graphics display calculator or maybe some graphing package like GeoGebra or Excel. Now, what I want you to do, if you're able to do this, find the peak of the infection, both when it occurs and the proportion of the population infected. Okay, so we'll do the fraction thing like you saw the graph before. Now, and then I want you to comment on how you think mathematicians may be able to take initial data and propose a model for future trends, and how would they adjust that along the way, perhaps? Okay, so we're developing the ideas quite quickly, and some people, if you're a junior mathematician, you won't go this far, but I want you to see the journey that we're on, and that there are formulas that mathematicians can use to work out what's happening. Okay, so come down here then, and I want to go to this question. Where are we in Australia now? Now, this is very latest news here. This comes from the ABC from Sunday, the 20th of April 2020. And here, what have we got? They've gone back to the total number of cases within countries. And here we have UK, Italy, Spain, United States. Now, obviously, if a country's got more people, you've got chances of more infections. I think we've seen that from our little discussion before. Here are our total cases and so on in Australia. But what I want you to look at is what about the shape of the curves? What about the shape of the curves, given what we've been talking about? Okay, what about the shape? And I'll take you down. There's another graph I would like you to look at, also coming from that news stream. And here, it's this one here. And it's gone back to how many confirmed cases that we've got on a daily basis. So there's a big peak up here. In there, there's a big peak on March the 20th. But since that time, it's come down. That's April the 12th. That's the day on which I screen clipped this. And so here, it's come down. The daily number of infections have confirmed cases has actually come down. Now, I want you to make some comment here about where we are compared to the other countries, the shape of the curve, and what we should do next, okay, about what's going on. And then we have a final slide for you to think about, and everybody should think about this one. What would this mean? Here it is. What would this mean? And what I want you to try and do, I've not put any scales here. That's a bit naughty, but I want you to focus on the shape of the graph here. Try to write down what would be happening if the infections follow the black graph. That's that one. And you can see it's composed of two other graphs. But this is what is going to happen, we're saying. And what would that mean for us here in Australia? Okay. And perhaps I would give you a little hint. Would it concern you if the graph looked like that later on? And in practice, how could this occur? What might happen for us to go into that sort of model? Okay, look, good luck with your investigations. And I really would like you to talk to family members and your parents about it and discuss that, see if you can understand some of the maths involved in the spreading of a virus in a very simple way. I hope to see something from you, so I would like to send it in. But cheers for now.